Hey everybody, this is my attempt to try to keep us from falling too far behind while I'm on jury duty. I know you're all really excited about learning more series stuff without me being there to ask questions, but this is what we got, so y'all are all going to be just fine, and we'll see how this goes, okay? Alright, so so far we have learned how to look for geometric series, and we have learned a couple of other tests like the ratio test and the root test and the integral test and p-series. And today we're going to look at two more tests that we are going to add to our repertoire of tests, more fun things to learn and figure out when to use. And this is going to be called the direct comparison test, which is probably, while the most straightforward of the two comparison tests, also probably the least useful. And the other test we are going to learn is the limit comparison test, which is by far my favorite of the two. In fact, I think it's one of my favorite tests to run. It's kind of like my go-to after I look for the nth term test, geometric series, and p-series. So the first one is going to be direct comparison. So I hope you can kind of see on my screen real quick. You can see that we are going to compare a series in question with a known similar series. They call it a parent series that is already convergent or divergent. So there's something really important about this. Okay, the one we are going to choose needs to be something we already know what it does. Either we need to know that it has this by it being a geometric series, and we already know that that geometric series converges or that geometric series diverges, or it needs to be a p-series test, one that we know either converges or diverges. And we need it, if it is going to converge, we need it to be bigger than the series we are comparing it to. Because what we are trying to say with this is that if this parent series converges because it is larger than the other series, then that means that the new series that we're looking at also will converge. Because if the one we already know is bigger and if it comes down to something and this other one is going to be smaller than it, then it will also come to a number. And remember, we do not care what it converges to. And then if it's going to diverge, right, then we want it to be smaller than the series we're looking at. So that way we can say, since this thing is going to go to infinity and it's smaller than the one we're comparing it to, then we know that the one we're comparing it to will also go to infinity. Okay, so those are the things that are the most important thing, is that the ones we're comparing it to, we need to, if we're going to have one that converges, we need it to be larger than the series we're comparing to, and if we are going to have one that diverges, we need to be smaller than the series we are comparing it to. Okay, so you can see here, it lists that out. If that thing converges and it's bigger than the other one as we get to infinity, then the other one converges. Okay, so let's just get to it real quick by looking at some of these ones that are down here on this sheet of paper. The first one is the series from 1 to infinity. So I'm going to see if I can draw this. And I apologize for the poor handwriting. No worse than on the board on a normal day though, right? It's supposed to be n cubed plus 1. Looks like two backwards C's with a gap in between. That's okay. Alright, so we're going to look at this series. Now this is something we don't know if it converges or not, and we can't use a ratio test necessarily to determine it, what's going to happen, because we'll get a ratio of 1. Also, it's not a geometric series, and the nth term test fails. We cannot use the root test. So we're really kind of in a bad situation with the tests that we currently know. So we're going to try to use our new test, which is the direct comparison test, okay, which I will kind of abbreviate DCT a lot of the times so that we there's more than one comparison test. We will also be learning the limit comparison test. Okay, so with the direct comparison test, we're going to want to think of something, normally a p-series. Remember, that's a nice, easy thing to do, because if p is greater than 1, we know it converges, or a geometric series. Okay, so when I look at this current one right here, I notice that it says 1 over n cubed plus 1. And I could tell you right now something about this series, 1 over n cubed. Because that is a p-series where my p is greater than 1. So hopefully you can remember that that means that this series converges. And also, since the one we're comparing it to up here, since it has a n cubed plus 1 in the denominator, that means that denominator is always going to be larger than my denominator for this p-series down here. So that means that if the denominator is larger, then this fraction will end up being a smaller number. So that means that this series, the one we're trying to compare to, is always going to be smaller than 1 over n cubed. And since it is always smaller than it, and this thing here converges, we now know that this series from 1 to infinity of 1 over n cubed plus 1 also converges. Okay, so now you can kind of see the gist of that test. Alright, so let's look at a different example. See if I can figure out how to clear this page or something.